made it out here. I'm just like,
Okay, here you go. Okay, so technical definition. First of all, y'all know what a function is. How do we know something's a function?
it is
Vertical line.
vertical
Yes,
line.
vertical line test. But technical definition of a function. It is a relationship between x and y such that each x corresponds to one unique y value, which is why it passes the vertical line test. So if the point 2, -3 is on the graph of a function, then no other point can have an x value of 2. However, it is possible for another point on the graph of x, f of x to have a y coordinate of -3, for example, 2, -3, and 5, -3. Y'all know all this. That's just a review of things you already know. Okay, so a one-to-one function
What is that, a function in such?
in which
In which, I'm sorry.
I think probably maybe in passing, I might have mentioned one-to-one functions last year, but we did not spend any time with them. Now, they're not difficult. A one-to-one function is a function in which each y value corresponds to only one x value. So, both things are true. Now, in order to be a function only, it has to have, each x value has to have one unique y value. This is the reverse statement. Each y value has to have one unique x value. So now, if you think about it, some of the things that we study that are functions are not one-to-one functions. For example, a quadratic is a function. It passes the vertical line test. But a function in which each y value corresponds to only one x value, on a quadratic, that's not true. Because if I drew a line right here, I would have two y values. And that's not what this is saying. It's one y value for each x value. So it's the reverse. So not everything that we've studied is a one-to-one function. We'll talk a lot more about it. Okay, so we're going to determine how we can tell if something is one-to-one as well as being a regular function. We already know how to tell if it's a function. It's if it passes the vertical line test. But the numerical determination okay, going to pull out a word from forever ago. If the function is discrete, what does that mean? You remember?
Ends. Or not connected.
Not connected. Individual points. So points not connected. I'll put that real quick. Those you've forgotten. Alright, you'll be able to tell if it's a discrete function, they're going to either give you ordered pairs or a table with just plotted points, or they like to give those, y'all remember mapping? They like to give you these like numbers like they do these things. And that tells you it's an ordered pair. Those are also discrete points, so that's called mapping. Probably haven't seen it in a while, but anyway, those are discrete because they don't give you an equation. If they give you an equation and you plug it in, it's going to connect the lines, right? But if they're discrete, the way you're going to tell is that there will be no repeated y values. However, if the function is continuous, which means it's connected, the way you'll be able to tell is that the y values will be always increasing or always decreasing. But not this whole decreasing and then increasing again. That would be a quadratic. A quadratic is decreasing and then increasing, and that is not a one-to-one function. So you're going to look for things that are increasing and then decreasing. Or increasing only or decreasing only, but not both. Okay, that's how you're going to tell numerically if all they give you is either a table of data or something like that. That's a numerical determination. The graphical determination is easy. In order to be a one-to-one function, it will pass both a vertical line test and it will pass a horizontal line test. So, example again, quadratic passes the vertical line test, fails the horizontal line test. But, for example, the square root function passes the vertical line test. It also passes the horizontal line test. Okay, does everybody understand? So it's the same test. Draw a horizontal line, and if it touches twice, that means it fails. If it touches more than once. All right. And then the analytical determination. Analytical determination, you're going to try to recognize the shape of the graph from the equation. So that is why we spend it's one of the reasons why, we spend so much time learning the parent functions. Because if you know what the parent function looks like, you have an idea, even if it's some sort of offspring from a parent function, you have an idea about what the shape of the graph is going to look like. And you're going to determine if the shape passes the vertical and the horizontal line test. If it passes both, it is a one-to-one function. All right, so the inverse of a function, which we did do inverses, is defined to be the function function that's formed when we switch the domain and the range. We did this in Algebra 2 frequently, but started it because my class just took a test on it. So we started it way back at the beginning of the year. But if you'll remember, the very first thing we did was we just took a table of data and we switched x and y. That makes the inverse. Then we got the mirrors out and we would put those on the linear parent function and we reflected it, so we graphically switched x and y. And then we actually switched x and y in the equation and solved for the new y. We've found inverses before, so that's kind of old news to us. That's how you find an inverse. What property of the function must exist in order for the inverse of the function to exist? Y. Okay. If f of x is not one-to-one, like a quadratic or an absolute value, those will not be a one-to-one function. I'll explain this in just a second.
Did you switch wood and after
Maybe.
I got it?
Yep. Yep.
I was like,
Sometimes my hand moves faster than my brain. Or the other way around. Okay. So we didn't really deal with this a lot in Algebra 2. If f of x is not a one-to-one function, so it fails the horizontal line test, then, because there are repeated y values, just like on a quadratic, we've got y values that are in the same place, right? So when the inverse function is created, remember that's going to be a reflection across y equals x, so it turns it this way. Then those repeated y values, these things up here, they become repeated x values. And that means this is no longer a function. So that means f of -1 doesn't exist. Not for this function, because it's not one-to-one. Now, we did these in Algebra 2. The inverse exists, but you can't call it f of -1, because that is a function. Does everybody understand what I'm saying? So you can make an inverse of this. It looks like this. But this is not a function. So you can't call it f of -1 of x.
Could you just call it maybe the inverse
You
of
could
f
call
of
it
x?
the inverse of f of x, yes.
Okay.
But it's not a one-to-one function, so what you get is not a function, and you can't use this notation. So, unless you alter the domain or range, which we may do some of. Okay. So, if it can be determined that a function is one-to-one, then the inverse of the function can be found. So we're going to fill in the following chart to describe how to find the inverse of the function if it is established to be a one-to-one function. This is review. You already know how to find inverses. So numerically, you would create a table. Already know how to do all this. To get a numerical determination, you're going to create a table for f of x, or they may have given you the table for f of x, and then you just switch x and y, that's all you got to do, and then you'll have f to the negative 1, or the inverse of f of x. That's what this notation means, and the inverse is a function because it's function notation. For a graphical determination, graphically, you would reflect the image across y equals x. Now sometimes that's easy to do. If it's real, like, they're lines or whatever, it's real easy. Sometimes if it's like curvy, it's hard to get it and make it look right. So the other option is to find critical points. On f of x and switch x and y. Which y'all know because you've had me before. I'm a terrible grapher. So this is usually what I do. I find a few critical points and switch them and then try to get a basic shape because I'm just not very good at drawing. So, okay. And then lastly, analytical determination, and this you already know how to do. Switch x and y. And then you solve for the new y. Okay, so for now, we are talking just about one-to-one functions. So if it is not a one-to-one function, you can't find the inverse, not right now. Because we're just talking about one-to-one functions. So before we do anything, we have to determine if the inverse of the function exists as a function. And then provide justification. If it does, then we're going to find the inverse. If it doesn't, you can't. Not right now, because it's not a one-to-one function. Okay, so they gave me this table of data, and I have to determine whether or not it is a one-to-one function. Now, we know how to determine that it is a function. We want to determine if it's one-to-one. So, it says, if the function is discrete, which this is, all we have are some points, the function is one-to-one if there are no repeated y values.
It does have.
It does
Those
have
two.
It does. It has 2 repeated y values, so I'm going to say not a one-to-one function. A repeated y value of 2. So, f to the negative 1 of x, d and e, that means does not exist. That d and e is a big, we use it in calculus and you can abbreviate it just like that. The whole calculus world is used to it. Okay, so the next one, again I have discrete data because it's just points. I'm going to check and see if I have repeated given y values?
No.
I do not. So this is a one-to-one function, so I'm going to write that.
Can it also not have repeated x values, or can it?
It shouldn't, because it's a function.
That's what I thought.
So this is a one-to-one function. So the inverse of f of x would look like this. That was easy enough. C, is C a one-to-one function? Yes, because it passes both the vertical and the horizontal line test, so it is one-to-one. All right, so now we can either try to reflect it across the linear parent function, right here, or you can take some critical points and reflect them. That's what I'm going to try to do. Like that, sort of. So I just took these 4 points and switched their x and y values and plotted them this way. Everybody okay so far? This part should be all review, so. D, is it a one-to-one function? No, because it fails the horizontal line test, so I'm just going to say not one-to-one. Fails the horizontal line test. So g to the negative 1 of x, d in e, does not exist. Is e a one-to-one function? Yes. It is one-to-one. I'm just going to take my critical points and plot them. So graphically, it's a reflection across the y equals x line. So it's over here. I just took my critical points and swapped them. Okay, so now we have some that we don't have the picture of them, and we don't even have any data from it. So this is where we have to imagine the shape. What shape is f?
Quadratic.
It's quadratic. So is it a one-to-one function?
No.
No, so that's all you have to put. Not one-to-one. It would fail the horizontal line test. So f to the negative 1 of x does not exist. G. What shape is it?
Linear.
Linear. So will a linear function of any kind?
Yes.
It will. So because it has, so yes, it's 1 to 1. All right, so now we have to find the inverse. So I'm going to write it first as y equals, instead of f of x. Now, switch x and y, just the letters, switch places. So now I have x equals 2/5 y minus 3. And now you are solving for the new y. You're getting the new y by itself. So I'm going to add 3. This next part you can do in 2 steps or you can do it in 1. You can either clear the fraction first by multiplying by 5, and then you're left with 2y, divide by 2. Or you can do it all at one time by multiplying by the reciprocal. It doesn't matter, you're going to get the same answer either way. Because I would like to be considered a mathematician and be efficient, I'm going to do it all at one time. 5 times 5, 2 times 2. I am going to go ahead and distribute this. And the last thing you have to do, because this is a 1-to-1 function, you have to put the f to the -1 notation back on it, so that we know that this is the inverse. Everybody okay? Any questions? Like I said, this should be pretty much repeat. H.
Square.
It's a square root function.
So
So it is 1-to-1. So I'm going to write it as y equals first, so then I can switch x and y. All right, now we're solving for the new y.
minus 4.
So first move the 4. It's hanging out there on the end. So I have x minus 4. Now what?
Divide both
Divide by
of these.
Very good. You can, and this makes no difference, it's the same either way. You can either divide each individual thing by 2 or divide it all by 2. I'm going to divide each individual thing by 2 this time because 4 is evenly divisible by 2. If it wasn't, I'd probably just draw the line because then you'd left the fraction, but this one won't be. So I'm going to do it like this. It's the same thing, it just simplifies it. All right, now what?
You have to square it.
Square it. In order to cancel the radical. Now, last thing is to subtract 3. Now, all of this stuff that's inside the parentheses happened before the minus 3, so it has to come after the parentheses. You could work all that out, but you do not have to. Because to work this out would involve FOILing and simplifying, and you do not have to do that. So all I have to do finally is to write it as f of x notation. Okay, so the as an inverse. So go ahead, take a second and just find the inverse real quick. Switch X and Y, find the inverse. Okay. Y'all get what I got? If you wrote it as 2x over 3 plus 4 over 3, that's fine too. It's the same thing. We all good? Yes. Okay. So now what they want us to do is compound functions. Remember, whatever's you're working from the inside out. So you plug this into that. So we're plugging the inverse into the original. I'm going to write them right next to each other. So here's my inverse, one I just found, 2x plus 4 over 3. And here's my original. Okay, now the notation up here has this on the inside. That means you're plugging all of this right here, where x is. So 3.
Oh, that won't be bad, that just cancels.
It's not bad at all, because what happens to your 3?
That's supposed to be a 2,
What's supposed to be a 2?
or maybe I'm thinking.
No.
Yeah, this
No,
one's...
Yeah, I see it wrong.
Okay. Okay, so my 3's just cancel. My 3 coefficient and my 3 that's on bottom, those cancel.
And then the 4's canceled.
And so I get 2x plus 4 minus 4 over 2.
And then you have
And then
x
4 over 4, that's gone. So I have 2x over 2
equals x.
equals x.
Wow.
Oh, that was easy. That's fine. Now, this notation has us doing it the other way. So again, I'm going to write them down next to each other because I just think sometimes it makes it easier to see.
And that won't be right.
It should be. This time I'm plugging all of this there.
So would you want us to rewrite it like 3 halves?
Plugging in. This time my 2's cancel. X minus 4 plus 4 over 3. Minus 4 plus 4 cancels. 3x over 3. And you're left with just x. If two functions, f of x and g of x, are inverses of each other, then there are two special composite functions that will equal the same thing. F of g of x should equal x, and g of f of x should equal x, if they are inverses of each other. So now, they've asked us down here to determine, by using this notation, if these are inverses of each other. So first we will find f of g of x. Then we will find g of f of x. and they should both equal x. So the first one they want us to do is we're going to plug g into f, solve it, and then we'll plug f into g. So let's go g into f first.
G is F.
Uh-huh. Well, that one worked.
Yes.
I got x. You still have to try the other one because it is possible that one composite will give you x and the other one will not. So you got to try them both. So now we're going f into x. That one works too. So yes, these two are inverses. Everybody okay? Now y'all do this one. If you did f of g first, plugging the g into the f, then you save yourself some time because it doesn't work. And if the first one doesn't work, you don't have to do the second one because the first one didn't work.
Why did I get that it worked?
Uh-oh. So let's see.
Y'all probably didn't do the two to both.
This one, that's what I'm saying. Did you do g going into f first?
Yes.
That would be 2x plus 1 over 2 minus 1.
Correct.
You have to get a common denominator.
Oh, snap. I didn't
And so when you do that, it doesn't work.
Oh.
I canceled out the 2's and
Can't do that
with x plus
because
4.
this fraction was a grouping symbol, so you can't cancel the 2's.
Oh, dang. Well then, either way, but f of x into g of x still doesn't work.
Doesn't work either.
Whether,
Yeah, it doesn't work, so.